We are live, and thanks to all of you that came today and are online. We will be able to take questions from those of you online, so if you have questions on there, we'll be monitoring the chat and also be able to pipe you in. And it's a pretty cool day we have here today. I know the crowd was hindered a little bit by the weather, so I thank all you for getting out today and getting here, because we do have a special combination. I usually try to keep the introductions a little quick, but we kind of have a trifecta of things going on today. And first of all, this is supported by the Shamshir Prakash Distinguished Lecture Series. And Shamshir was the professor here. I want to get my numbers right. From 1978, an associate professor, and then he retired in 2000, but stayed around and was active for quite some time. In addition to setting up this lecture series, he also has a Teaching Scholar Award here, a scholarship, and a lectureship through ASCE as well. So he's been very supportive of his profession. Shamshir had several contributions to the field, particularly in the geotechnical earthquake engineering area, and he was really recognized for his advanced soil dynamics and liquefaction work early in his career. He conducted some really pioneering research on liquefaction of silts and clays, and then he's probably best known for his international case studies conference that I think Craig spoke at in the past, numerous times probably. And I think he held 14 or 15 of those conferences around the US, and it was truly an international effort. And upon his full retirement, years after he retired as a professor, ASCE actually picked that entire series up and still hosts it to this day in his name. So thank you, Shamshir, and his wife Sally for setting this up. Shamshir is currently in India at the ripe old age of, I think, 92. Wow. And he is going to try to catch this on a recording. And Craig is also here as part of the Kappe Lecture Series. So the Kappe Lecture Series is from the the American Academy of Environmental Engineering and Science, formerly known as just the Academy for the most part. And it's named in Stanley Kappe's name. He was a very successful environmental engineer back in the earlier days. And he really felt like he owed a debt to the profession that was so good to him. So he set up this lecture series that goes nationally and picks one distinguished lecturer per year. And he was the executive director of the Academy of Environmental Engineering from 71 to 81. So we're thankful that Mr. Kappe set up this lecture, and that supports Craig being here as well. And that brings us to our main course, Dr. Craig Benson. He's a geoenvironmental engineer with a lot of expertise in waste management, and essentially known as the foremost authority on waste containment and waste stabilization processes, perhaps in the world. With his focus on environmental containment of solid, hazardous, radioactive mining waste, and, as we'll learn about today, beneficial reuse of as much material as possible, he's really reached the pinnacle. He's a member of the U.S. National Academy of Engineering and actually chair of Section 4, I believe.
I was. I just retired from that.
Just moving off of that. So not just a member of the Academy, but truly a dedicated leader of the Academy as well. He's also a member of the National Academy of Inventors and a fellow of many societies across the board that I'm not going to get into, but most notably the American Association and for the Advancement of Science, AAAS fellow. He's published more than 300 refereed journal articles and has a tremendous number of research awards, including being listed as one of the Kappe lecturers. So congratulations on that, Craig. Dr. Benson studied civil engineering at Lehigh University and then completed his MS and PhD at the University of Texas with classmates, roommates of one of our Academy members, Chuck Shackelford, as well. And in that, always try to find out one unique thing. Craig was an active, competitive barefoot skier earlier in his career, and he was a very active mountain biker until a geotechnical aspect kind of ended his career, and that was a soil off of a crash crushing his shoulder. So, apropos, soil ended his biking career. So, with that, Dr. Craig Benson.
Thank you. Appreciate it. It's nice to be here. You're lucky to be at such a wonderful institution. I've had a great day talking with lots of different people. There's a lot of energy and activity here, and I can only imagine how exciting it is to be part of it. So you're lucky. I'm going to talk to you today about something I'm passionate about, an area I still practice in considerably, and that is how we manage historic coal combustion waste from generating electricity. But just a little bit of background. I spent most of my career in academia, but I've never been an ivory tower academic. I always think of myself as a practitioner academic, the way I was trained in graduate school by practitioner academics. Academics that did translational and applied research with the objective of getting ideas out in industry about how we can solve complicated problems or do things better. It wasn't about writing a journal article that some other professor was going to read and cite, but it was about doing work that was going to change the way we went about our engineering practice. And I think of that, that's really what impact is all about, and that's what my career has been about. I've been at University of Wisconsin. I spent an early part of my life there, both as a faculty member in various leadership roles, and then later as Dean of Engineering at the University of Virginia, and I retired from both of those institutions over the last few years. And that's why I have the title emeritus. Now, faculty around here probably know what that title emeritus means, but a lot of people ask me, what does it mean? I'll tell you, it means two things. You get to use your email address forever. Big deal, right? And you get to work for free. For free. You can still come do your work in your lab and not get paid. It's as good as it gets, right? But you don't have any schedule, which is really good. But my career at two different institutions has been, one of the great things about it is I've been able to work with people in the industry on really interesting, practical, pressing problems. Yesterday, I talked about another problem when I was at SLU that we've been able to work on for the last 20 years, solving a really challenging problem for industry. And this is another one. This is one that actually affects all of us in this room, whether you know it or not. And we'll talk about a little bit about why that is. We've got lights on in this room. It's comfortable temperature. Where does the lighting come from? Electricity, right? We got electricity, right? We run our laptops, right? They run off electricity, right? Where does electricity come from? Out of the wall, right? I think half my neighborhood thinks it comes out of the wall, right? Where does the electricity come from? Ultimately, yeah.
Sadly, I believe around 60% of power in the state of Missouri comes from coal.
But it comes from a power plant, right? And maybe, yeah, but and coal-fired power plant is one of those ways that we generate electricity, right? We have to have a plant of some sort to convert some type of thermal energy into electrical energy, right? Some way of converting one type of energy into electrical energy. And coal's one way we do it, right? And when we burn coal, historically in the old days, we would just burn it, and it would all go up in the air and into the water, didn't even worry about it. And then we realized that created a lot of air pollution, water pollution, and we started collecting the ash from burning the coal and disposing it. And now we're starting to rethink about, well, we were doing that to protect the air, but now is that protecting the water? And are there some things that we need to do differently to be able to protect our water resources? And as a person who's always tried to think about as an engineer, I'm trying to make things better, not just do things because somebody told me to do them, but actually make things better. I ask questions like, well, are the things that we're being asked to do really make sense? Are we actually benefiting the environment? Locally, globally, we have to be asking those questions. That's some of what we'll be talking about today. We're also going to talk about if we have to move some of these out, and the primary topic will be about if we're going to have to take out some of our historic ashes that we managed using historic practices, can we use them for other applications? And does that actually, is that just oh. That's shocking. But does that actually promote sustainability? If we're going to use those ashes in some other way, is that actually beneficial or not? And we'll talk about that. So we begin with what is coal ash, or perhaps a better title I like to use is coal combustion products. So we have a power plant and we burn the coal. And when we burn coal, we generate so-called fly ash. That's the fine particulate that goes up in the exhaust stack, up to the atmosphere, and we collect that. Electrostatic precipitator, a bag house, we collect that fine particulate material. That's this stuff up here in the left, and this is a particle size curve. So those of you who have been in your geotechnical courses, this is percent finer, and this is particle size. And the fly ashes are in the silt fine sand, but predominantly silt size all the way over to the clay. But they're typically are very fine, powdery type materials in the silt size particle range. And this is just some examples of fly ash. You can just look like powdery materials. That's what we're catching that's going up in the gas. We're collecting that with either electrostatic precipitation or with a bag house. Coal-fired utilities generate lots and lots of fly ash as they burn coal, because if you had a fire in your fire pit, when you're burning wood, you see the fly ash come up. The same thing is happening in a coal-fired power plant. The other thing that we generate from that process of burning coal is bottom ash. So we generate larger particulate that are too large to essentially move up in the gas stream and float, and they'll drop to the bottom. That's so-called bottom ash. That tends to be more on the fine gravel to sand size, maybe down in the silt too, but falls into this size of a particle size curve. But you look at bottom ash, it looks like gray sand, all right? Looks like gray sand. And we'll collect that as well. Another thing that we generate often today at power plants, because not only are we concerned about this particulate, but what else is in the exhaust for the flue gas from a coal-fired combustion?
Greenhouse gases.
Greenhouse gases, right? And what else? That's a good one. What else is in there? Everybody remember about acid rain? Right? Acid, yeah, sulfur, right? So we burn the coal, we have sulfur in the coal, we'll burn that coal, and that releases sulfur into the flue gas. And if we don't capture that, we didn't generate acid rain. So we'll capture that sulfur as well. That's called so-called flue gas desulfurization residual, or FGD. We have to have a good acronym for everything. That's also fine textured sludge type material. Just a photograph of that as well. That tends to be a hydrated calcium sulfate. So these are the products we're talking about. Coal ash in the upper left, bottom ash in the lower left, and flue gas desulfurization solids. And we're really going to focus on the two on the left for materials to use as supplemental cementitious materials. That's a lot of words to say, in concrete. We'll talk about what that means. Now, there's a lot of different ways to manage coal ash, but two are predominant. One is called dry disposal. We'll talk about that in a minute. That's less problematic, but we have dry ash and we put it in a landfill. But a more common technique, particularly in the eastern United States and the southern United States, but some right here in the Midwest, and I bet there's some here in Missouri, is so-called hydraulic disposal of coal ash. So you think of, we have a boiler, we're burning the ash, we're generating flue gas, and we're removing the fine particulate from that with a system. We have bottom ash that's being generated at the bottom of our boiler, and we convey that ash with hydraulic techniques. So we just essentially rinse it out with water, put it in a pipeline, and pump it out to a pond. I think of it kind of like as hosing off your garage floor, the particulate off your garage floor. It's not a lot different. You take essentially fluidize the particulate, put it in a pipeline, and send it out to a wastewater treatment basin. Often you'll have the bottom ash, the fly ash. Sometimes the sulfur removal will be commingled with that. A lot of power plants have tried to separate that as well. You may actually have the rest of the wastewater streams as well at the power plant, all going into that same pipeline. It goes out from the power plant back here, goes by a pipeline, and it goes in to create this beautiful pond, right? Now that's not really a pond, it's really a wastewater treatment system, right? We'll have water coming in on the right-hand side here, and then it's migrating through the pond. Often these ponds are designed so the water takes a circuitous path, and as it takes that path, it's moving slowly, and the particulate in it drops out, all right? So the ashes, the fly ash and the bottom ash drop out and settle into the bottom, right? And some of that water that's in there seeps out of the bottom of that disposal facility as well. And then the water at the tail end goes out to a river or a lake. Well, generally a river though. This is very common in the southeastern United States. Big power plants located right on a waterway, and they feed water for the plant comes in from upstream, and the wastewater goes back into the river downstream. And that wastewater coming out of the pond needs to meet NPDES requirements. Does anybody know what that is? NPDES? Besides Joel? Somebody that's taken one of his classes? Somebody's taken the wastewater class? I'm taking a surface water class?
National Pollutant Discharge Elimination System requirements.
Yay! You can nay. You can nay. Yeah, that has to meet essentially a water quality requirement on the tail end. So it's a design treatment system. It's not just pumping it into a pond and then letting it go. It is a design treatment system. And all those solids, though, not all of them, but 99.9% end up in the pond. Very little of it actually goes into the river. And this is the way we did this for years and years. We started doing this in the 1950s when we started collecting the ash because we were worried about air pollution. And now we're seeing maybe that wasn't the best idea to manage it with this strategy, all right? So one other strategy that I mentioned is dry ash disposal. That doesn't help with plants where we've had hydraulic disposal, but some utilities moved to dry ash disposal, essentially limiting that hydraulic system, just collecting the ash and then burying it in a landfill, just like we would have for municipal solid waste or other types of waste streams. Just another example. These are in really great places to go visit, and these are in the mountains often of the eastern United States. Just fantastic, beautiful area. Okay, so this got done for years and years. Now, recently in 2015, new regulations were passed called the coal ash rule. In part, does anybody remember something in the early 2000s happened that was with a sluiced coal ash basin, one of those ones like I showed earlier, in Tennessee?
Yeah, Tennessee.
Yeah, we had a catastrophic slope stability failure. I think it was Kingston.
Quite a situation with fly ash being considered a contaminant.
Oh, yeah.
Just back in a lot of applications of fly ash and concrete.
Yeah, for years and years, right? That was a catastrophic failure. I think it was on the Tennessee River. And it's one of these berms on one of these facilities failed, and all the fly ash went right into the river. And of course, when things like that happen, all hell breaks loose, and EPA and Congress passed new rules. In fact, it was interesting when all this was going on, we were talking about making coal ash a hazardous waste at that time, which would have really changed the rules. It's not a hazardous waste, it's a solid waste, but it's not hazardous. And I actually got to testify in Congress about how that rule ought to be formulated, which is really a lot of fun. If you ever get called to Congress, say I'll go, because it's a blast. Now, that was 2015, and we came up with a whole bunch of new rules. And then in 2024, those rules got revisited. And with the so-called legacy rule was passed, the 2024 legacy rule, which had additional implications specifically for these basins. Now, prior to that rule being passed, these were being managed in a particular way. They were being closed under the old rule, which said that you needed to stop operating these facilities, and you would decant the free water off the top, right? So I'd pump that off, right? And the water comes down, and then I would build a cap over top, essentially closing it to limit the ingress of water long-term. And that would be my closure strategy. That was a legal closure strategy up until 2024. And a lot of utilities in the East followed this strategy. They closed sites using this approach. They decanted, they built a cap on top, they were done. And the idea was, once you've done that, then it's, this water inside is slowly going to go through so-called drain down, right? And then ultimately reach an equilibrium with just a little bit of release to groundwater, right? That was the plan, and there were many of these built. And then people changed their mind, right? Maybe that wasn't such a good idea. And what the legacy rule promulgated in 2024 said that this was a fine closure strategy, provided that none of the poor water in the coal combustion products was so-called free water, or it could be mobile. Now, try to find how free water is defined in any of your true engineering or physics textbook. There's no free water. This is a regulatory definition. It's not a real definition. But what it said, and what it implies, though, is that particularly if I had any of my ash below the water table, where it might have poor water migrate through it, that was no longer allowed. Even if you closed it in place and it's been signed off on by the state government, sorry, you're not done. You are done, but you're just going to have to go back and excavate all this and move it somewhere else. All right? That's what the 2024 legacy rule did, all right, required. And the large primary approach to that is we'll go build a new landfill nearby with a modern engineered lining systems, which we know work extremely well, but we'll build one of those nearby, and then we'll excavate this out, we'll dry it some, and then we'll drive it down the street and put it in a new landfill, all right? And the idea is to protect the groundwater, all right? And you're starting to ask yourself, does this start to make a lot of sense? I'm going to build a new landfill down the street. It's going to be environmentally protective. They have a great track record. But I'm going to build all that. I'm going to dig this up. I'm going to move it down the street, cap out the new one, and things will be better. Now, we ought to be asking ourselves, is that better, or are there better things that we could do? And just to give you a sense for this, I'm working on 3 of these different projects right now in the Southeast. What do you think it costs to do that? To move one of those, build a landfill, move a basin? Just take a guess.
Anywhere between $10,000 and $100 trillion.
That's some big bounds, right? Anybody else want to guess? Roughly about what they cost each? Somebody guess, come on. Not even close. Typically, they're about $3 billion each. $3 billion each with a B. A B each. Each one is 3. So you do 3 of these, it's $10 billion, roughly, right? A little round off error in there, right? Where does that cost go? Goes on your electric bill, right? Yeah, so you, as a customer and as a citizen, you ought to be asking yourself, is this the best thing we should be doing? Does this make the most logical sense? And actually, are we having any improvement in the environment, right? So we'd be asking ourselves, does that make sense? So a couple other things we could do. That's essentially, this solution is gone, right? That's no longer. Are there some other things that we could do? So option 1, as I mentioned, is construct a new landfill, like I'm showing over here on the right, modern engineered landfill. We'll excavate our old material and we'll move it over to the site. Another option, if we are going to move it, is maybe we don't landfill it, maybe we process it and reuse it for something else as a cementitious material. We use conventional fly ash and concrete. Who's had that in their concrete materials class? Everybody can't deny this, right? And some of you had concrete. I thought I saw a hand over here. Yeah, we have a volunteer, right? We use fly ash and concrete all the time, right? Improves the quality of the concrete. Maybe we could harvest ash, process it, and use it as a so-called supplemental cementitious material. And does that promote sustainability? This is what this ash looks like, sluiced coal ash. It's in a basin. This looks like a sedimentary deposit, doesn't it? If you're in geoscience, that's because it is. Now, it's not a natural sedimentary deposit, but it is a sedimentary deposit. It's ash material, different types. Over time, the coal source changes, operations at the plant change, the characteristics of that ash changes, and we get something that looks different over time. We get different layers, but that's normally consolidated, nearly saturated coal ash in one of these coal ash basins. Here's a sample of it taken with a Shelby tube. You can see it's saturated. This is in a tube sampler, one in my lab. We've spent a lot of time trying to characterize the hydraulic properties of these materials to put into all kinds of nifty models. But that's what it looks like. There's another example. You can see the layered structure just from different changes in the coal or operations at the plant. And this, what you're seeing here too is ash that's being harvested. They're actually going in and excavating it out over time. Now, just to provide a little context too, you saw that pond I showed earlier. The size of these ponds is enormous. These may be 300, 400 acres in size. They're big. And a power plant might have 1, 2, or 3 of these. So this is a big excavation project, lots and lots of ash. How can we do this and do something that's actually promoting sustainability, right? So we're thinking about, if we do this, can we somehow reduce our energy consumption in our society? Can we reduce our greenhouse gas emissions? Can we reduce other environmental impacts? One way to do that is to look at this as a partial replacement for Portland cement. We don't think of Portland cement as a major source of greenhouse gas emissions, but it is. It's a really substantive source of greenhouse gas emissions, and we'll see why that is in a minute. But about 8% of global greenhouse gas emissions come from producing Portland cement concrete. That's an enormous amount, nearly 10%, 8%. It's a large quantity. If we could alter that in some substantive way, that would be a real win, right? That would be a real win. And we can do that by partially replacing some of the Portland cement that goes into concrete with ash that we either get from a fresh power plant or ash that we exhume from a basin and process. We call that ash that's used to replace some of the Portland cement a supplemental cementitious material, or to make it easier to say, we call it an SCM, right? Because saying supplemental cementitious material 20 times fast is hard, right? So taking some of that cement out and replacing it with the ash will improve, or could improve, our the sustainability metrics of our concrete. It also has some other practical benefits: increased concrete workability, durability, compressive strength. I'm not a concrete material scientist. I read that, I'm reporting it. If you have any questions for that, we'll have one of your other colleagues here talk about it, all right? But these are a lot of global greenhouse gas emissions. So we have a way of putting a dent in that. But that's only true. If I could replace some of that cement with this material, it's only going to be beneficial if actually the processes of excavating it, processing it, and getting it all ready to use in place of Portland cement doesn't generate more greenhouse gases than the Portland cement itself, or require more energy, right? I have to do it in a way, I have to evaluate whether I'm actually going to get a reduction in greenhouse gas emissions, recognizing all the things I've got to do to get it ready to go into the cement. Where do the greenhouse gases come from? One of the things I love about civil engineering and many parts of engineering is all the brute force things that we do. You know, we do all these analyses in class and mechanisms and calculations, but so much in practice is big brute force things. And one of those is how do we make Portland cement. We take limestone, lots of beautiful limestone in this area, by the way, right? I saw some of it this morning when I was out for a hike. We take clay, the limestone gives us calcium carbonate, clays give us aluminum and silica, and then we'll also add some iron in as well. Sometimes we get that along with the clay, depending on the bar source. We take all that material and we put it into a cement kiln, right? And where I grew up, we had lots of these cement kilns right around where I lived. So I was very familiar with these. And this is a brute force process. We put into this kiln, it's a big tube, it's rotating. All that particulate is in there, and we're firing it in the end. We've got a flame injected in the end, all right? We're putting energy into it. And what are we doing with that energy? We're doing so-called calcining. Essentially, we take that calcium carbonate, that's what limestone is, and we blow that molecule up. That's how we blow it up, right? We create calcium oxide and calcium dioxide. That we just take the energy from that fuel and use it to break that guy up and create these two products. And at the same time, we're blending in these other components, and we create so-called clinker. And clinker is essentially the base material for Portland cement. We then grind that, and that creates Portland cement, all right? This process essentially creates 8% of global greenhouse gas emissions. Where are the greenhouse gas emissions coming from? Really simple. we take that limestone, right? It's got carbon dioxide in it, and I heat it up to blow it apart, right, to create the lime and carbon dioxide. There's your greenhouse gas right there, right? Boof. And also all this, right? All that combustion that's going along with it, which is normally fired by either oil or natural gas, sometimes with waste solvents are used for it as well. So we could potentially avoid some of that by replacing the cement with so-called supplemental cementitious materials like the ashes. So the SCMs are silicaceous, aluminosilicaceous, or calcium aluminosilicaceous. We got silica, aluminum, and calcium, powdery-like materials that we can use as a partial replacement for Portland cement in our concrete, all right? And fly ash is this silicaceous particulate. It's this fine particulate. We talked about it being silt-sized, but the particles aren't like soil particles. They're not angular or rectangular, or angular would be a better description, but they're more spherical particles from the combustion process. We can also use these as a cement kiln feedstock as well, but we're going to focus today on just using them as a replacement for concrete. Why might we be interested in this? Well, we've been using fly ash in concrete for years and years and years, and we always had an abundant source of it coming from coal-fired power plants. Early in my career, when we were working on different uses of fly ash, I realized there was a whole commodity market based around collecting ashes from power plants and selling it into concrete production, right? Train loads full of fly ash being shipped around the country from utilities to power plants. But what's happened about coal-fired power plants over time? Up until now, we never know. We might be building lots of them next year.
Now for other energy sources,
Yeah.
including natural gas.
Yeah, we're winding down coal-fired power plants, right? We used to have most of our energy was produced by coal-fired power plants, and now it's less than, I think, 40%. And it's decreasing every year, and that's probably not going to change, despite politics. We've got an abundance of natural gas in this country. We've got more natural gas than anybody. We produce more than anybody in the world. At some locations, it actually has a cost, a negative cost to the producer. They would like to have a market for it. So we're probably not going to see coal come back. And so you look at the coal, the ash produced over time, that's the black line. It's been dropping because we're closing coal plants. And our ash being used has remained pretty steady. And if you extrapolate this over time, we're going to get to a point where we don't have enough ash for concrete. And we use ash in concrete all the time. There's lots of good things that benefits to it. So we need to have other sources. So potentially this is a viable source for that, is to use ash from these ponds and from landfills, excavating it and putting it right back into our concrete stream, if it makes sense. And this is actually going on in significant efforts, particularly in the eastern United States, but some in the West as well. Just some examples of these work that we've been doing for EPRI. There are state mandates both in Virginia and North Carolina to excavate those existing basins outside of the legacy ash rule. These states have essentially told their utilities all those basins will be removed. The others will be doing it shortly after this, now that the coal ash rules, the new legacy rules in place. But you can see all these different stars are places where harvesting is being conducted, all right? They're exhuming it and processing that material to use in concrete. But you can't just dig it out of the ground and use it right away. You've got to dig it out and you've got to process it so that it has the properties like the C618 ash that we would normally use and regular dry fly ash coming out of our plant. We've got to excavate it. We've got to dry it because it's saturated, right? It's been placed under water. We've got to often do some particle size processing. We have to grind it so that it meets ASTM C618 requirements for concrete. We'll have to often do a so-called carbon treatment. These ashes were put in place, just sluiced in, right? Or that's sluicing is the industry term for hydraulic disposal. And they include unburned carbon. They may include carbon amendments that were meant to pull other things out of the exhaust, the flue gas, like mercury. Those carbon treatments, that residual carbon that's in that ash, really has negative impacts on the concrete. And our concrete materials, people can tell us more about that later, but we've got to remove the carbon, right? And that takes energy. So all these steps I do to process it take energy, they take work, they generate emissions. And the question is, after I do all that, does this make sense, right? Is this going to be better than just using plain old cement alone, or better than using conventional dry fly ash, right, out of the plant? So that's the question. Does this really contribute to sustainability if we're doing it? And so we did that using a tool called life cycle analysis. Who's used LCA or has learned some of that? Got some good volunteers, right? We got LCA volunteers. So we did a life cycle. Essentially, people originally called this pollution counting. But you're going through all the processes and examining how much energy am I using in each step, how much greenhouse gas emissions am I using in each step, how much water am I using. Sometimes I'm looking at how much toxicity I've induced into different water supplies. We'll look at some of that a little bit later. But it's essentially an accounting tool to look at different impacts on the environment. And we use that to quantify both greenhouse gas emissions, or GHGs, and non-renewable energy consumption, or energy impacts, what it took to process the harvested ash and to use it in concrete. And then we did that same thing for not only just to process the ash, but then we did an analysis. Once I looked at a meter cubed of concrete, was this still going to be beneficial? Not just comparing fresh dry ash from a power plant to harvested ashes, but actually once we got it into the concrete as well. We'll look at it both ways. Basic requirement is that the ash has to meet ASTM C618. Not all ashes are going to meet that, even if we do all the processing. They may not have the right chemistry. So that's one thing immediately we have to look at. We're going to assume that any ash that we would process for this application at least has the basic chemical requirements. But there's particle size requirements, there's carbon requirements, and those other requirements require processing that take energy and create emissions. So we do that with an LCA, and this is we're going to have several busy graphs, but I'm going to talk you through them. But we need to look at the different steps in this analysis, and we look at what's called a system boundary. Essentially, we draw a box around the different unit processes that we need to consider in our operation, and we'll analyze our impacts inside that box, the system boundary. And so in this example, for example, fresh coal ash, right? I've got two different ways I can look at that box. I could have this fresh coal ash coming out of my power plant, and I could look at this dash box here where I'm just taking that, and perhaps I'm doing some particle size adjustment, I'm doing some screening, some grinding, maybe doing some carbon treatment, and I'm creating some C618 fly ash that I could use. I might also consider that if I'm using that fresh ash, I don't have to build a landfill, right? I don't have to put it in a landfill. So I could have a landfill avoidance credit as well. So I might make that boundary a little bigger and have it go all the way up around here. So it's not only evaluating the processes to get the ash ready to use, but also the advantage of not having to build it and put it in a landfill. I do the same thing for my harvested ashes, all right? I'm going to look at each of these processes down here, and I'm also going to acknowledge that I'm not going to build that landfill we talked about, right? That I'm not going to build that. I'm not going to excavate these and put them in landfill. I'm going to excavate them, process them, and send them into concrete plant for use as in place of Portland cement. In that case, I've got all these different processes to consider down here. I've got excavation. I'm going to have to exhume that material. I'm going to have to dry it. I'm going to have to particle size. I'm going to have to screen stuff out. I'm going to have to grind it. I'm going to have to do carbon treatment to remove the residual carbon that creates a ton or 1 megagram of ASTM C618 ash. Now the particle size adjustment in the basin coming out of that, that's been in the hydraulic disposal, a little different from what we would do in the plant. The plant's pretty easy. I generate fresh dry ash. I do some sieving on it, maybe a little bit of grinding. But when I'm hogging out that stuff that's been in a basement, in a basement, I call it. I'm digging that out. I'm digging out ash, but I'm digging out old trees. Maybe I'll find an old tractor in there. There's all kinds of things. These were built in the 1950s and operated until now. There's like everything that's been in your basement is in one of those basins as well. So there's a lot of other, it's more than just what we would do for fresh ash. There's a lot of junk that goes along with it. For each of these processes, we go in and examine each one and look at what are the greenhouse gas emissions from that process, what is the energy consumption, and then we add them up and we examine that, we compare it to cement alone or fresh ash alone. Now, there's a couple different ways you can do that. And I think there's what I would say there's a right way to do it and there's a not so good way to do it. What I see a lot in the literature is people set up this problem and then they'll just buy a piece of software and they'll take a database that's built in that software and start typing, right? I don't think that's the valid way to go about doing this type of accounting. The way that I go about it and the way we did in this particular project is I got an industry cohort together that I interviewed. Different people are actually in the practice of doing this. And we were doing this through EPRI, which is the Electric Power Research Institute. So these were essentially all their members, their industrial members. And we interviewed them and we had them do detailed accounting of the different unit processes at their plants. So we actually got the actual energy numbers off of their operations at their harvesting plants. So we could do a really fair, careful evaluation of what the energy use was. We got the fuels that they were using as well. How much diesel, how much propane is being used, how is it being burned, and we know then we could apply emission factors to that to get greenhouse gas emissions from it. So we tried to make this as industry data grounded as possible. We spent the first half of this project was all about meeting and talking with people from industry and gathering their data. This is also one of the things that's great about working with EPRI. You've got all their partners. They all are interested in helping. It was a blast to just talk to each one of those, a lot of fun. But we created what's called a life cycle inventory, which is just all this data. But we made it as real as possible from actual harvesting plants, from people in practice doing this kind of work. Once we have that, we stick that into a so-called LCA model. It essentially just takes all the data and starts to add it up for you. It's a nice, convenient tool. You can do it yourself in a spreadsheet, but you can use a piece of software to do it more elegantly. We use SEMA Pro. That's a very well-known LCA software. And we used primarily, most of our data came out of our industry database, but a few things we had to add from other databases. The US LCI database, the EcoInvent database, and EPA's WARM database as well, just for some things we didn't have data for. But we took all of our LCI, we put it into that software project, and we had it calculate these different impacts from different processes. So for example, we had it calculate the greenhouse gas emissions from excavating the ash, whether we were excavating it from a landfill or from an impoundment, and this is per ton of ash we're producing at the end, all right? Interestingly enough, for example, excavating it from a landfill requires 4 kilograms or creates 4 kilograms of carbon dioxide or carbon dioxide equivalents, whereas from an impoundment, 7.7. Why would I generate more greenhouse gases from excavating it out of an impoundment than excavating out of a dry landfill? It's heavier, full of water. So I'm in there excavating it, and half of my mass I'm pulling out, maybe not half, maybe a third, is water, right? That I don't even want, right? But I got to pull it out. That's not true in my landfill. I have very little moisture in that as well. In fact, at the dry ash landfills that are being harvested, they actually use it without even drying in most cases, which is pretty remarkable. But yeah, so it just takes more work, right? And same with the energy. You can see excavating it out of our basin or impoundment uses twice as much energy. The drying process is very energy intensive as well, but you can just look through these different metrics. We went through these for each case, processing, whether screening it, grinding it, and then we looked at different carbon removal techniques. We used so-called thermal treatment. Does anybody know what thermal treatment is? That's a very elegant word for saying I'm going to burn it, right? I got carbon in there. I already burned carbon at my power plant. All right, I'll just burn a little bit more, right? I'm going to burn off the residual carbon in the coal, and you can pull some of that heat from that back, which is good. We can use some of that in the drying. And we did that for low carbon, 6%, 12% carbon ashes. We used another thing called electrostatic treatment. So essentially, we run the ash on a conveyor belt, which has charges on two different sides, all right? And essentially, by that charge difference, it will pull the carbon out, the carbon particulate out of the ash. That's electrostatic. Not quite as efficient a carbon removal as I get with thermal treatment. And then there's another technique called chemical treatment, where I apply essentially a surfactant to the ash, and it bonds onto the carbon faces, essentially the carbon surfaces, blocking those surfaces for interaction with, for example, air and training agents in a cement. So I could do chemical treatment, electrostatic treatment, or thermal treatment. And again, we did all the analysis for each one of these. And these are all based on industry data, not stuff I made up or got out of a database from a piece of software. This is all out of industry information from their plants that they're running. All right, what did we find? And these are busy graphs. I apologize for that, but this is about as simple as they can get, and I'm going to walk you through them, all right? We're going to look first at global warming potential, or greenhouse gas emissions, all right? This is kilograms of carbon dioxide equivalents per megagram or ton of C16A ash that we're producing, all right? And on the left, we're going to step on the x-axis, we've got different processing techniques. We're going to step from the left side, which is I'm just taking fresh ash out of a power plant. I'm not harvesting. I'm just looking at a power plant, right? I'm taking that fresh coal ash, and I'm going to use it straight away. I don't even have to process it. And then I move from left to right. Okay, maybe I have my fresh ash and I have to screen it. I have my landfilled ash. I have to screen it. My ash from an impoundment or a basin, I've got to screen it. Then I'm going to be screening it and adding grinding in, then adding chemical treatment or electrostatic treatment or thermal treatment. And in each case, as the bars get bigger, that means my total amount of greenhouse gas emissions through processing the ash is getting bigger, all right? So as I do more processing, I'm going to generate more greenhouse gas emissions. That makes sense, right? I'm going to be doing more stuff to it. First of all, over here on the left, fresh ash. It's negative. How can that be? How can my fresh ash have a negative greenhouse gas emission? Recognizing that the black bar here is avoided landfill credit. I'm going to give myself some credit that I'm not even going to put that fresh ash in a landfill. I'm going to, instead of using that standard approach of landfilling it, I'm going to be taking it out and putting it right into my as a replacement for Portland cement. I don't have to build that landfill. I don't have to operate that landfill. Those are greenhouse gases that have been avoided. So we actually have a negative number for fresh ash alone. Now, if I have to screen that, I got to add, there's a little bit of work for screening. That's the bright green, all right? And that adds a little bit of greenhouse gases, all right? It gets bigger as I go to landfilling or pulling it out of impoundment. I'm using more and more energy, and I'm creating more greenhouse gas emissions, a lot of it from the drying process, a little bit of it from screening. As I go forward, I keep adding more. You can see I've got the purple here is excavation, and the blue bar is the drying, and then I've got screening, and then I've got grinding on top of that. And then I've got my chemical treatments, and this is where it really tends to change. If I use thermal treatment to get rid of the carbon, I generate an enormous amount of greenhouse gases, right? Why is that? How am I getting rid of the carbon? I'm burning it just like I was in a power plant, so I generate the same greenhouse gas emissions I generate from burning coal, all right? If I use an electrostatic treatment, that's where we're using electric charge to pull it out. I do have, that's the little orange bar that's been added on top. I do add to the total, but it's pretty modest. It's just a small bump in greenhouse gas emissions. If I did chemical treatment, it's a small bump as well. That's the little yellow bars at the top, all right? So where's, outside of the thermal treatment process, where are most of the greenhouse gas emissions coming from in preparing this material to use as a supplemental cementitious material? Looking at these bars and the color of this legend. Drying, right? When I'm drying it, I'm spreading it in windrows. Essentially, I'm spreading it on the ground and I'm turning it, I'm moving it. Yes, ma'am?
Oh, I was gonna say after drying, then it would be grinding,
Yeah.
chemical, screening, and then finally electrostatic.
Yeah, the grinding is one of the big ones, right? That's the dark green. Why is grinding? How do you grind this stuff? Has anybody been to an industrial grinding operation? Got we have actually big rollers, right? Run by big electric motors. And you pour the ash through, and it's just brute force processing, and it just crushes it. But I've got big electric motors running it. They run off electricity, which comes from the power plant, which comes from coal, right? So that generates a lot of energy, and also screening is as well. I've got to put it on a screen and I've got to shake it. That generates a lot. But the big guy here is if I do thermal treatment, I generate a lot of greenhouse gas emissions. If I don't, I use one of my other strategies that are pretty modest. That's an important lesson learned. I can go through that same analysis, essentially more processing, higher the global warming potential in that system. How much energy do I use? Little different story here. Fairly similar as I walk through, right? More steps, more energy requirements. But remember I talked about how the thermal treatment was the big greenhouse gas hog, right? But when I move over and look at from our energy consumption, it's the lowest, right, of the different options. Why is that, right? Well, the energy's in the carbon, right? I'm burning that, essentially the energy that's in the carbon, so I don't have to add energy to it. Whereas my chemical treatment method, I got to actually produce that chemical. I got to pump it in there. It takes energy to do that. My electrostatic treatment, I have to run electricity through it. It takes energy to do that as well. But it's more processing, more energy, but not quite as dramatic as we see for the greenhouse gas emissions. But that carbon treatment is the one thing I talked about. It's the opposite there. So that's all about making the ash, and I guess what we look at there, that hasn't said it's actually better than anything. It's just giving us a sense for what it takes to make that material. Clearly, one thing that comes out of that, there are significantly more greenhouse gas emissions associated with using harvested ash relative to fresh ash. Because remember, fresh ash was negative, right? So it's not as good as fresh ash. The question is it good enough? So let's look at this in terms of using it in concrete and look at the greenhouse gas and emissions associated with creating and implementing different concrete mix designs. We looked at a number of different compressive strengths. These have odd numbers here because these were in English units converted over to SI. We need to stop using English units in this country. Just use SI. Come on, move over. Yeah. I mean, life would be a lot simpler. And then we looked at 4 different levels of cement replacement, from none, no ash, up to 40% of the cement being replaced with ash. And we looked at producing 1 meter cubed of concrete. And we looked at essentially using fresh ash alone, harvested ash with minimum processing, harvested ash with maximum processing. And then I looked at different carbon treatment scenarios, fresh ash with electrostatic treatment, harvested ash with electrostatic treatment, fresh ash with chemical treatment, harvested ash with chemical treatment. We just stepped through these different processes and looking at all the different unit processes to create 1 meter cubed of concrete. So this was fresh versus harvested on the left, just comparing them 1-to-1, and then looking at different carbon treatment comparisons. This is what we get, another busy graph. But we're looking here on the x-axis of different options like I showed in that previous slide, and then the y-axis is the ratio of the greenhouse gases associated with a meter cubed of concrete with one of the ash percent options, replacement options being considered relative to the greenhouse gas emissions for producing concrete with cement alone, no ash in it at all, all right? So that ratio is less than 1. That means what? If that greenhouse gas emissions for making concrete with ash in it normalized by concrete without ash, if that number is less than 1, what does that tell us about our greenhouse gas emissions? It's lower, right? If it's less than 1, it's beneficial. That's a good thing, right? What do you see about all these different options on this slide? How many of them are greater than 1? None. None of them are greater than 1. They're all less than 1. Some are even smaller than others. Yes, sir?
So are you using bottom ash in this study, or is this ASTM class C? What type of fly ash are you showing this
Yeah.
for? Is it
Good.
different in different?
Yeah, this is a fair question. Question is, am I using fly ash alone or bottom ash or both? And we've made 2 assumptions. One, we've got commingled ash.
Right.
We will grind that to meet the particle size criteria in ASTM C618. And we will use ash that meets that, the chemical composition requirements in C16.8. So I've made that assumption, all right?
Okay.
If it doesn't meet that, it's out, all right? So we're assuming it has that basic set of properties, all right?
I'm only asking that because if the calcium content's higher, that's gonna, give you more bang for your buck.
Certainly.
In terms of concrete
Certainly.
properties.
Yeah, we haven't done that refinement in it,
Okay.
but you would do that. But the couple things you see here. One, all of these options are more sustainable, right? They generate fewer greenhouse gas emissions than using regular cement alone. So all those are viable. My harvested ashes, if I compare some of these boxes, that's 20%, 30%, 40% fresh ash. Here's the harvested ashes. They're a little bit higher, right, as I go to harvested ash, because I got to put more energy in. I don't quite get the sustainability bang from a greenhouse gas emission. But are they that much different? Not so much. There's not that much additional energy and effort put into harvesting the ash that would push it to be so much different from fresh ash from a greenhouse gas emissions perspective. As for the fresh ash and then the minimum and the maximum, yeah, it gets worse in the worst case scenario, but even in those scenarios, I end up with, I'm still generating fewer greenhouse gas emissions. This is all beneficial relative to using Portland cement alone. The best case is fresh ash, but harvested ash in each case is beneficial from a greenhouse gas emission perspective. When we look at it more broadly, the different types of carbon treatment, for example, they're not that different, but the thermal treatment is the one that's the least beneficial in terms of greenhouse gas emissions. But these, here's fresh ash with, these are electrostatic treatment. Here's with the chemical treatment. They're really not that different at all, right? They're nuances. The key thing is all of these promote greenhouse gas reductions, all right? Even despite having to do all that work to excavate it, process it, treat it, it's still sustainable. And we get that same story from the energy component as well. All of these ratios are less than 1. Yeah, they vary a little bit from process to process, but they're all less than 1. So this is harvesting and processing ash for use as a supplemental cementitious material sustainable? Yes, from a greenhouse gas emissions and energy consumption perspective. This is a much better thing to do than landfilling, right? It's not quite as good as fresh ash, but at some point we're going to run out of fresh ash, and this is the next best thing. I just want to close with a couple slides here. What if we excavated it and transported it to a landfill? If we did that analysis, and I looked at 3 different cases, a baseline case where we did nothing, close in place, which we have been doing, and closure by removal, doing the whole process, all right, putting it in a new landfill. I'd go through that same process, did some groundwater modeling, looked at impacts to groundwater, used that as some of the inputs, and this is some of the outputs from our similar types of life cycle assessment techniques, all right? left bar in each one of these is do nothing. The middle bar is close it in place, what people have been doing, and the right bar is excavate and landfill. Which one of these options creates the most greenhouse gas emissions? Excavate and landfill, right? It's by far generating the most greenhouse gas emissions. What particulate matter? This is deaths from particulate matter from diesel exhaust is a huge issue. We don't even think about that, but Jonathan Holmes at Wisconsin's done a lot of work on this, looking at particulate impacts on health, and it's amazing how the significance of diesel emissions. Which one of these creates the most deaths from particulate emissions? We're trying to protect people's lives, right? Put in, excavate and put in a landfill. How about kilograms? This is, I'll skip over here a little bit. Let's get over to ecotoxicity, looking at fresh water. Which is worse? We're trying to protect water, right? Actually, when we look at it from a broader perspective, we actually have more impacts on water from excavating and putting a new landfill. Why is that? What do I use in all my trucks to move this stuff to a new landfill, to excavate it and move it? Diesel, right? Is diesel a clean material to produce? Have you been to an oil field or an oil refinery? No, it has really significant impacts. So each one of these cases, no matter what we look at, we end up with the same conclusion. By far, the greatest impacts on people and the environment is the preferred solution in our regulatory code, right? And we're spending $3 billion per site to do it, right? You gotta say, does that make sense? So what are our conclusions? From a greenhouse gas perspective, energy perspective, certainly using the harvested ashes is a sustainable pathway. It's not quite as good as the fresh ash, but it is a sustainable pathway. It's much better than just putting it in a landfill. The carbon treatments have some nuances. The carbon treatment we choose has some nuances. So that's going to change some of the impacts. But in a broad sense, it is a sustainable approach. And the same thing's translated when we look at it ash alone and we look at it in the concrete, in a meter cube of concrete, we come up with the same conclusions, right? It's more sustainable to use, it is a sustainable process to use the ash, whether it's fresh ash or harvested ash, in the concrete than to use Portland cement alone. So some very simple conclusions. This is actually excavating it, harvesting it, and using it as a supplemental cementitious material is a good thing, right? That's having benefit to the environment. Perhaps the worst thing we can do is excavate it and put it into a landfill. We're doing that under the guise of trying to protect the environment, protect groundwater. And we probably do improve groundwater quality in a little patch of land, but our broader impacts are enormously different. And this is one of the things that gets people very frustrated with regulation is oftentimes things are done with a very narrow lens. We create rules with a very narrow lens without thinking about what are the broader implications of this. And we should be expecting that broader implications when we're making national policy. All right, well, I want to thank EPRI for funding this. This is a blast to do. I love doing these projects, working with industry and trying to come up with some practical conclusions that are relevant to all of us. So thank you. I know we're a little bit past 4, but I'd be glad to take some questions. If you got a skedaddle, that's okay too, all right? Yep. Any questions?
Sure, I'll start.
Start, great.
Have you done anything with trying to recycle the metals that are in this ash? Like
Yeah.
Gallium, germanium,
Yeah.
arsenic that we need for our photovoltaics and other green.
I have not, and not too much of that going on in industry, but one of your colleagues is working on that, right? Aren't you working on some of the metals removal from, and behind you in the back?
That's still in process. We found that in some of the ashes, they do carry some kind of valuable metals,
Yeah.
like a rare earth element.
Yeah.
And we found some gallium recently from a
Yeah.
very nasty ash from the tunnel. So we're trying to extract it out before using it.
So I think that's kind of this next wave, is to find ways to to get these minerals that we desperately need and want to create supply chains for before we put it into concrete where we're not going to get it back from, or put it in a landfill, right? The challenge is to do that in a way that we can make it competitive, right? So that's the analyses that have to be done. But fly ashes are loaded with metals. Another part of my life, the other thing, we look at all the different redox sensitive elements, how they're leaching out of fly ashes. Why are they there? Why are rare earths in there? All the stuff, the coals came out of the earth, right? It's the same place where all of it comes from, right? Yeah.
And when you burn millions of pounds of coal,
You create millions of
parts
pounds.
per billions comes into tens of thousands
Yeah.
of.
Lots and lots of it, right? Yeah, very good point. Yeah.
Well, in a number of European countries, of course, they use every bit of fly ash that they produce, and, I guess they don't always have as many coal-fired plants as we do. And I know in Canada, they're going back to a lot of landfills and they're reusing the material. And some of that fly ash is extremely high quality because of, when it was
Yeah.
when it was stored. I guess you talked a little bit about declining energy production from coal-fired plants in the United States, and you also showed kind of the usage, the percentage of the usage. When I started working with fly ash in the 90s, we were much less than 50% usage. I'm curious, did you look at any long-term projections of when you think in the United States will use all of the fresh ash that's produced? And then, are there any projections where you think we won't be really producing any
When we're out of ash.
fly ash?
Yeah. This is a really good question because this supply chain doesn't go on forever either.
Right.
Once you've excavated these, they're done, right? We did look at that, and I knew somebody was going to ask me this today, and I couldn't find that in my notes, but I do have it somewhere. There is an estimate, but it's decades, way out. But, there's going to be a point, not in my life, but in some other folks' life, when we will be out of that too, right? Hopefully by then, we've got some really nifty new energy sources, and we don't worry about any of that stuff anymore, right? Yeah. Yes, sir.
Yeah, so in one of the bar plots, that you show is all the ratios are below 1. That means carbon reduction.
Yes.
Is the cost per unit reduction already factored in, or is just a purely carbon reduction and the cost is another story
Yeah.
that we need to look at?
This is a great question, right? And you've hit on a key issue that I did not talk about. In fact, we haven't done an economic analysis in this. This is strictly a sustainability analysis, but it is more costly, right? Because if I got all those steps, it's going to cost more to generate that harvested ash than it is going to be to create fresh ash. But I'm going to have to do almost all those steps regardless, based on where the coal ash rule is right now. I'm still going to have to excavate it. I'm still going to have to dry it. I might not have to grind it. I'm going to have to move it down the street. I'm going to have to build a new landfill. So all those costs are embedded in something I'm going to have to do already. And so I'm not adding any additional cost, but it probably is going to be, that ash is going to be more costly if I tallied it all up. But I'd much rather almost give it to somebody. Even if I spent $10 a ton to create it, I'd almost rather give it to somebody to use in their cementitious material operation than to build a landfill and store it for the rest of my life when I'm going to have to monitor and be responsible for that landfill forever. So economically, it still makes sense, given that you're going to have, some of those costs are sunk whether you like it or not, right? Because by regulation, I'm going to have to do some of these things. But I haven't done that broader economic analysis.
So some industry may be more interested in looking at fresh ash, reduce carbon more, but it may cost more. But some other reduce carbon less, well, maybe for the same amount of money, I can, because it's cheap, I can reduce more.
Yep. Yeah, there's going to be trade-offs like that, where you're going to say, this one's got a lower price point, and I'm just going to go with that, right? But in a lot, the cost of a lot of these materials, given that a power plant operator is doing this, they've got all that cost already, they're almost going to give these materials away, right? So they're almost going to be free. So those costs don't go over into the concrete industry, they stay with the power plant. But it's just, that analysis is going to be very pragmatic. Everybody who uses this material is going to look at what their cost of operations are, right? Always, yeah. And they're going to do it in a way that's most cost effective. Yep, yeah, good question. Others? Other, yeah?
So, not necessarily on the cementitious side, but have you looked into like what the remediation is once they've like excavated all like the fly ash? Like, is that like land that people can set it back on?
The old land from where the basin was will never be used again for conventional human use. They are brought back to industrial standards for contaminant levels, but they would be only for, nobody's going to clean them up to residential use standards. There's just not going to, it would be way too expensive. Yeah. Good question. And the other side of it too is most of these sites have contaminated groundwater around them, but it's not, most of them have small plumes. They may go 50 meters off the limits of the basin, but they are in violation of groundwater standards, right? So that's got to be cleaned up as well, right? So you're going to have to pump and treat that or do something to it. And that's another sunk cost that we're going to, and another set of energy and environmental impacts we haven't even touched. Yeah. Yeah, good question. Others? Want to go to the bar?
And if we do have a few questions, we will go to the bar. First, let's thank Craig for his time today.
Thank you. Thank you for sticking around too. A little bit after 4 here.
And we do want the questions to continue. So we've got a reception set out just outside the door. Everybody's more than welcome to hang around for a little bit and save the hardest questions for Craig out there. So please join in afterwards. And thank you again, Craig, for an excellent talk.
Yeah, thank you for coming. Appreciate it.